It's my great pleasure to be here to introduce you guys my latest research direction and what my lab is currently working on. So the topic today is multisensory AI for personalized healthcare, and I will quickly introduce what I mean by this. So let's first take a longer look back to 60 years ago. And this photo shows a nurse using a mechanical watch to take a patient's pulse. And back then, pulse reading was only possible with the help of a clinician, and it was often inaccurate due to manual errors. And now, 6 years later, we have made this tremendous progress. And not only we have better medical devices, and they're increasingly powered by recent advances in AI or artificial intelligence for this automated and scalable health assessment. And however, when we look back, although we have witnessed this huge progress over the past decades, there's still multiple gaps exist. So first, clinical visits scheduled by people are occasional, and the intervals between two visits are often several months or even years. And that's a problem because it means diagnosis can be significantly delayed. And a lot of times, we don't catch diseases until they reach advanced stages. And this is even exacerbated by the huge dark space in healthcare that are never observed by any clinicians. And this is what creates a so-called time gap. In addition, because of this shortage of clinicians, hospital care was limited to a small group of people, and not everyone can easily access healthcare resources, causing a location gap. And further, when it comes to these AI-powered technologies, AI models often perform poorly on the subgroups that are often underrepresented in our training data, and causing this individual gap across different populations and domain shifts. On the other hand, we have a huge amount of personal and physical devices or sensors around us, and they passively collect our health metrics, such as your gait, your heart rate, your breathing, your sleep, and almost anytime and anywhere. And what if we can turn these everyday devices into intelligent health sensors using AI and uncover the so-called dark spaces in our personal health and give actionable insights? And imagine with these AI-powered everyday devices, what if we can get your physiological vital signs, such as your breathing and your heartbeats or oxygen saturation, just by looking at your smartphone or laptop without any physical contact? And what if these smart devices can even go further and do complex disease diagnosis based on these common multisensory signals? And what if this can be done even before the actual clinical diagnosis happens? And what if these smart devices can further do complex, also read, not only diagnose the disease, but also track your disease severity and progression based on your everyday manner in a completely passive mode. And they can further identify your personal behaviors, such as your medication response, and help you personalize and adjust your medications in real time. So this is what I'm going to talk about today. So my lab at UCLA, the Health Intelligence Lab, works on these interesting frontier directions at the intersection of AI and healthcare. So first, on the health and medical side, we want to build AI models that can enable new biomedical discovery and enable this universal health intelligence. For example, we have built AI-based biomarkers for chronic diseases like Parkinson's using novel signals, and from early diagnosis to tracking its severity, progression, and medication response. And to enable universal medical access, we integrate these AI models with daily sensing systems for longitudinal sleep and activity tracking and also built LLM-based interactive conversational agents for personal health insights and AI coaching. And to achieve this, on the machine learning side, we aim to build general-purpose health models to learn and reason from large-scale multi-model data, including wearables, physiological signals, and other medical modalities to enable these new capabilities. And finally, we design better learning algorithms for high-stakes health AI deployment of these models and making sure these models are robust, are fair, and generalizable when they're actually deployed to real world. So in this talk, I'll briefly discuss two directions our lab is actively working on nowadays under the broader scope of multisensory intelligence for healthcare. And first, I'll start with how to use our daily sensory data to build an AI-based digital biomarker for specific disease, Parkinson's disease. And on the second half of the talk, we'll move beyond specific disease types to build general-purpose foundation models for wearable sensor data that are capable of doing many disease predictions and even interpret and generate these insights in human language. Okay, so let's dive in for the first part, and we'll be discussing this early diagnosis capability of Parkinson's disease with our daily sensory signals. So we all know Michael J. Fox is one of the most well-known TV show and movie star with this famous Back to the Future series. And here is an interview video by Michael. So from this video, we can clearly observe his irregular body movement and these hand tremors. And in fact, this is because Michael was diagnosed with Parkinson's disease, or PD in short. So what is PD? Well, PD is the fastest growing neurological disease in the world. And over 1 million people in the States and 10 million people worldwide are living with PD as of 2020, which results in an economic burden of $52 billion per year. Unfortunately, a key difficulty in Parkinson's is that we cannot diagnose it in time. So in clinics, this disease is typically diagnosed based on motor symptoms like tremor or rigidity. However, these motor symptoms often show up many years after the disease onset. And by the time a clinical diagnosis is made, the disease has already been progressed for decades, causing non-reversible damage to our brain. So the challenge here isn't just to identify Parkinson's once it's visibly affecting someone, like this picture on the right. So the real goal is to have the foresight to detect this disease early on, before someone even has any clinical signs. And people have thought about how to get these foresights for decades. And over the years, researchers have studied CSF, neuroimaging tests, and blood chemical evaluation as potential biomarkers for early detection. While these markers have shown pretty good diagnostic accuracy, they come with significant drawbacks. They're invasive, expensive, and require access to specialized medical centers. And as a result, they could hardly diagnose disease in the early stage. So we asked ourselves, could we find a biomarker that's both accessible for regular daily use while also being as accurate as these clinical methods by aggregating this longitudinal data? So the answer is yes. And we have developed these AI-based systems that analyze our nocturnal breathing signals, i.e., your breathing signal during sleep, to detect Parkinson's disease years before these traditional clinical methods. And here's how our system works. We capture breathing data either from a breathing belt worn by the subject or use a wireless device that transmits signals to analyze the breathing. And with either method, we're able to obtain a full night of breathing data. And after capturing the nocturnal breathing, we design an AI model to learn and extract disease information directly from this data. So the model has two outputs, whether the person has PD or not, and assess the severity of the condition based on the clinical gold standard measure. So how did we do it? And recall that we want a model that takes in the full night breathing signal and output whether the person has PD or not. So let's focus on this binary classification first. So to construct our model, why not begin with classic methods, say a support vector machine or SVM? So we tried this, and here are the results. So on our test set, this SVM model achieves an AUC, which is a measurement of accuracy of just around 0.5. And for those who are familiar with this measure, that's essentially random guess. So clearly, we need to go deeper. And what if we turn to the state of the art in deep learning, like transformer models? Unfortunately, even with these advanced neural network models, they perform just marginally better than random guess. So what's the blocker here? So in fact, there are several key challenges that we need to address in this modeling process. And first, the input nocturnal breathing is high dimensional with tens of hours, whereas the output about the disease, i.e. the binary classification, is extremely sparse. And in this task, we're essentially trying to infer one bit of information from a very high dimensional and dense input. And this sparse supervision problem poses a very classic challenge in machine learning, which is overfitting, where the network might focus on irrelevant features in the data while learning nothing related to the disease. So our question becomes, how can we regularize the model training to actually let the model to learn PD-related information rather than some shortcuts? So our solution is inspired by the link between Parkinson's and our brain activity, as Parkinson's is a neurodegenerative disease. And in fact, when we go to sleep, our brain activity fluctuates throughout the night, which can be quantified by our brain EEG signals. So based on different frequencies of our brain waves, we can divide the EEG activity into 4 frequency bands. And different EEG activities are associated with different physiological functions of our brain, which naturally provide useful information for Parkinson's. And at this point, you might wonder, because our input or the signal we're interested in is breathing, so can we actually link breathing to EEG, or can we actually predict these EEG signals from our breathing? So the answer is yes. And we show that just using your nocturnal breathing signals, we can reconstruct this EEG activity throughout the night with pretty high accuracy. And such a prediction task could bring natural dense supervision for our model. And specifically, instead of predicting this disease information, we propose to add another prediction head to reconstruct the brain EEG activity from our breathing signals. And this essentially forms a multitask learning framework where this EEG prediction serves as an auxiliary task to regularize the model training and to regularize the model to learn PD-related information from EEG. And indeed, by integrating this auxiliary task, we see a significant improvement in our model performance, from this chance level to an impressive 80% accuracy. And in addition to this, there are also multiple challenges when we aggregate dataset, and I don't have time to cover those details in this talk, but happy to follow up offline or after the talk. So let me show you some results to get a better sense. So we create this large-scale dataset by collaborating with many institutions. And in total, we have over 700 PD individuals and over 7,000 participants. So with our AI model and customized algorithms, we can achieve pretty high and robust diagnostic accuracy for all this tested data, as well as for all different test modalities, such as breathing belt, or just use wireless signal to collect your breathing signals. And each bar here is evaluated using a live-on-out evaluation protocol, which means the model developed never see this testing data. And the most interesting aspect of this project, I would say, is the model also show initial evidence for early disease diagnosis. So in our dataset, we identify a group of patients who were diagnosed with Parkinson's 6 years later in the clinic, but they were not diagnosed 6 years before clinically. And we have data from these cohorts, from these 2 visits, like 6 years before and 6 years after. So what we do is we directly test our model on this early cross data. And first, we collect age and gender and other comorbidities matched control subjects, also from the data that collected 6 years before, and show that our model can successfully classify them as normal people. And further, when we tested on these prodromal PD patients, we see that the model is able to get the foresight to diagnose them early. And one limitation, as you can see here, is that we have a small amount of people in those prodromal set. And the next step is once we have this model, we may be able to identify people that are in early stage so that we can actually do testing or recruitment into clinical trials for drug development. And in addition, although I didn't cover this in the technical part, but our system is actually able to also detect the severity of PD with a high accuracy. And on the x-axis here, you see this MDS UPDRS, which is actually a clinical gold standard measure of PD severity. And the higher the score, the severe the PD, the Parkinson's is. And we compare here our model prediction to this clinical gold standard metric and find that the prediction shows pretty high correlation with statistical significance. And here's the exciting part. Once we can evaluate severity once we can evaluate the severity by monitoring breathing daily at home, we can even track the disease progression in a very fine-grained manner. So let's say a patient we monitored for over 1 year using our system. So traditional clinical measures of PD severity are usually done every 6 months. However, they're very infrequent and can exhibit high variances. For example, you can read from the score at month 6 that significantly deviates from the baseline. And we know this is impossible given Parkinson's is non-reversible. And now let's take a look at the predictions from our model. So our approach offers a more robust and more frequent assessments, and this provides a much clearer picture of the disease trajectory. And this, in general, can let us understand this disease progression pattern on a much more personalized level and customize the monitoring, and care for the patient in real time. All right, so that's the first part on this early diagnosis of this specific disease, Parkinson's, using our daily sensory signals. And now we move on to see how we can build these general purpose foundation models for wearable sensor data that go beyond a specific disease. And rather, we train a model on large scale data, and then we can adapt it to many downstream tasks. So today, we're drowning in sensor data. And one of the most ubiquitous sensor is the smartwatch or wearable, which can continuously and accurately capture our vitals. And this includes your heart rate, your respiration, your blood pressure, and even your oxygen saturation. So as we can see from the first part, this is really exciting because more than 0.5 billion people on Earth have a wearable. And if we could deploy such capability, it could be so-called universally accessible and enable this in-home and contactless triage or screening. However, this is still far from being scalable or intelligent because although we're drowning in sensor data, we starve for insights from them. So what do I mean by starving for insights? Let's take a look at one specific example. So traditional sensor analysis requires domain expertise to interpret patterns. And here I show a daily multi-channel sensor dataset. You can see the x-axis is time from midnight to noon to another midnight. And each row here is a specific sensor feature derived from wearables, such as your heart rate from the PPG sensor, your accelerometer or steps from the accelerometer sensor, etc. And as you can see, wearables can capture our physiology and behavior continuously. While these raw signals are hard to understand, it will be very useful if we can turn them into meaningful, human interpretable insights about your sleep, your activity, your anomaly events, and eventually turn into health suggestions or coaching. And in fact, this is pretty critical for our user engagement and generating insights and potentially do interventions. So we ask here, how do we interpret the sensor data? And can we make this sensor data interpretation as readable as a news article in natural language? So let's imagine. So drawing an analogy to computer vision system, we can describe the scene and context in an image with natural language, such as a cat or a dog. What if we can translate these raw numerical streams of sensor data or sensor readings into clear descriptions, such as reporting the statistics of your metrics, identifying unusual patterns in your readings, and generating events with their associated time periods. So in this work, we develop a family of foundation models called sensor language model, or sensor LM in short. Specifically, once we have this multi-model daily sensor data streams, we design an automated way to create descriptive text captions for sensor data at scale. So this leads to this largest sensor language dataset to date. And once we have this sensor data and the caption pairs, we further design a flexible multi-model pre-training architecture that connects these two modalities and connect specifically the sensor patterns to our natural language description. And by using this architecture, we can enable multiple downstream capabilities of this model, such as we can do zero-shot sensor understanding by using textual prompts, or doing retrieval or alignment with arbitrarily sensor and text input, and we can further generate descriptive sensor captions just by inputting your raw signal data. And here we show a comparison of sensor LLM to state-of-the-art LLMs such as Gemini or Gemma, or the state-of-the-art self-supervised learning methods such as SimClear or Dino. And overall, we can achieve pretty competitive results on different tasks such as zero-shot, few-shot, or retrieval tasks, as well as across a variety of application domains such as activity recognition, sports, hypertension, or anxiety detection. So even before we move into the details about the model, the first question we have in mind is, how can we describe your sensor data? So we propose here a hierarchical sensor caption generation technology. And this involves 3 levels of granularity for describing your sensor data. And here for simplicity, I just show 3 channels of your verbal readings. For example, your heart rate, your accelerometer data, and your wrist temperature. And the x-axis is the time in minutes. So first, given this time series, we want to describe the basic statistics of your signals, such as their mean, their minimum, their maximum, or standard deviation. And we refer this to our first level of caption called statistical caption. And beyond these statistical measures, we can also describe this trend or anomaly based on sensor readings, such as highlighted in this red box, like accelerometer data drops between this minute, and there's a peak of heart rate happening at this specific time frame. And we refer this to the second level of caption, which we call structural caption, that aims to describe your sensor patterns and trends based on the multi-channel data. As you can see, the example caption we created includes a peak heart rate is detected at minute blah, 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 and from minute to minute, the accelerometer shows a decreasing trend. And finally, from users logging or some ground truth data collection, we can identify periods of actual context meaning, such as you're sleeping during this period or you're performing an elliptical event. And we refer this to the third level of caption, which is called semantic caption. And this describes the contextual meaning of your activities, your sleep, your mood events, etc. For example, we describe both the sleep and their associated time frames where the event happens. And once we have this caption generation strategy, we can further derive this large-scale sensor text dataset from raw data that collected in the Fitbit study. So in total, we collected more than 2.5 million person days from more than 100K people. And this results in around 60 million hours of sensor data, and the diversity is pretty large across more than 100 countries. And compared to previous studies on sensor and language modeling, our dataset is orders of magnitude larger, and our sensors is more comprehensive. And this is critical for us to derive new insights and enable large-scale modeling of this sensor language model. So let me jump into what this model can actually achieve. And first, I'll talk about this very interesting capability called zero-shot prediction. So traditionally, when you have a foundation model, you will need to fine-tune this on a specific cohort data to be able to classify a specific downstream event or disease such as Parkinson's. However, using sensor LM, once you have your sensor data input, you can directly input your text prompt such as biking here. And the model will return with a probability event over whether the sensor data is paired with this text prompt. And here, for example, if the model returns the probability of 0.89 for yes, then we can confidently say that there's a biking event happen in this sensor data. So this enables this capability of classifying and understanding new sensor data without any retraining. And quantitatively, we compare our SensorLM model with state-of-the-art large language model, which also exhibit this zero-shot prediction capability. And we focus on this 20-class activity classification. And the input text prompt is basically the activity event, such as running, biking, etc. And on the x-axis, you'll see multiple tasks where we are actually performing, like in addition to the activity classification, which is the first column. We also group them into different categories, such as identifying the environment, like whether you're performing this, whether the context is within, is indoor or outdoor, or like underwater, or like in the land. And we also do fine-grained event classification within the gym cardio scenario or within the outdoor sports scenarios. And overall, compared to existing large language models, our models show pretty high zero-shot prediction capability, and that can actually generalize across multiple categories. And in addition, the second capability we show is the zero-shot sensor and text retrieval. What is retrieval? Basically, given a sensor data segment or given a sensor data input, we should find the best description, the best text description over a text database. For example, if you have more than 1,000 or more than 10,000 text prompt, we should be able to retrieve the actual description for this specific sensor data. And the vice versa. For example, we can also retrieve a sensor data based on query caption. Specifically, for example, here, we want to retrieve or we want to find over a database which individual will have sleep apnea. And by just giving a sensor data in a sensor database as well as the text prompt, we're able to do this task in a zero-shot manner, and we can find and search the right sensor data from this text description, and vice versa. So qualitatively, I show here an example. Still, like we use the previous example and showing the heart rate, accelerometer data, and temperature readings. And here we also show the high-level conceptual events that happen, like sleeping in the first 6 hours, and then the user do a treadmill and strength training after they get up. So over a database of 10K or 10,000, more than 10,000 text prompts or text captions, we're able to retrieve the ground truth caption, and we show the actual retrieval similarity given by the model. And this SC is the similarity score. So the highest similarity score is the actual ground truth, like the run was recorded between these minutes, the treadmill event was recorded between this, and the sleep took place during this period. And very interestingly, we find this model is also able to capture the semantic meaning in this language space and able to associate with sensor data. For example, we select 2 similar captions that with moderate similarity scores. And by looking at the caption content, it's very interesting. So we are able to either identify the correct event, such as sleep, like if you look at the caption 1, we're able to identify the correct localization of the event, such as there's an event actually happened in the first period, and there's an event happening between minutes 4:30 to 4:40. but the event type is wrong. Like basically, we're not able to identify the running or strength training, but incorrectly describe it as walking. And in contrast, for another similar caption, if you look at similar caption 2, we're able to identify the correct event, such as run, treadmill, or strength training, but the localization of the event is incorrect. And finally, we show a dissimilar caption where it has both incorrect event as well as the incorrect localization of the event. So this is pretty interesting, and it shows that the model actually learns both the event contextual information as well as how to localize those events. And quantitatively, we compare SensorLM with this state-of-the-art zero-shot LLMs by comparing this retrieval at 1 or retrieval at 5 accuracy. And this is based on a data set with 100 examples of 5,000 samples. So despite these numbers, like we show pretty high accuracy of SensorLM in both cases, I also want to highlight these dashed lines, which indicate that these LLMs can actually is not able to perform such a task. And this is because of the inherent limitation of their context length. If we have a 5,000 sample database, we need to input those data into the memory of the LLM so that it can retrieve. But however, the reality is neither we can input all the 5,000 samples, especially for the sensor data, or if we do it in a multi-turn level, the model will easily forget the context. So it's not able to perform the retrieval task. And similar to traditional machine learning models or this transfer learning of recent foundation models, we can also extract this sensor encoder standalone and fine-tune it in a few-shot setting to adapt it to some downstream task we care about. And this will give us, and this actually shows that SensorLM can generate better sensor embeddings for tasks with very limited label data. So here we compare SensorLM with state-of-the-art self-supervised or self-supervised methods that train a foundation model, such as SimClear, Dino, or MSN. And specifically, we chose tasks that we want to adapt to, such as predicting whether the person has hypertension or not from their wearable data, whether the person has anxiety or not from their wearable data, or like in general, predict activity from their wearable data. And as you can see on the x-axis, the training label per class is very limited. And for hypertension and anxiety, which is a binary classification task, basically means we only have 5 or 10 samples per data set. And as you can see, the model actually provides a pretty good prediction for future setting. And this is also consistent across different categories. And more intuitively, we show here a confusion matrix where each row here is an activity and each column here is the prediction of that activity. So ideally, if your model is performing well on multi-class classification, you want to see the diagonal to be highlighted. And basically, you're predicting the correct class, and you're not confusing them with different classes. And by comparing with SimClear, which is a state-of-the-art self-supervised learning method, we show that our model is able to achieve this pretty good prediction with both sensitivity and specificity and achieve a pretty good visual look of this confusion matrix. And finally, one of the most interesting and important capability is we can generate this sensor report in natural language from raw sensor data. And what I mean by this is you can just input your raw sensor data to the model and then insert a start token or you can imagine like there's no prompt you need for the text encoder, and automatically the model will generate a descriptive text that cover both statistical information, structural information, and contextualized information about your sensory data. For example, here we show, again, like a multisensory example from in an afternoon to midnight segment where the person performs outdoor biking in the afternoon and go to sleep around 11:30. So ground truth caption we will generate for this data is there are two outdoor biking events happen between these two time frames, and there's a sleep event detected from this time frame. So let's first see if we input this sensor data to Gemini and what it will generate. And obviously, neither the model is able to identify the correct events, and it confuses outdoor biking with walking, nor it can generate the actual time frame that the event is happening. And by looking at sensor LM, we show that we're able to detect the correct event, like outdoor biking and sleep, and also localize those events with pretty high accuracy. And also, there will be inaccurate cases, as you can see here. We also detect walking events, but this showcases the capability of the zero-shot caption generation, and this will also help many downstream tasks. As you can see, this will unlock very interesting conversational capabilities by just inputting this, again, showing this information to the user and interact with the chatbot. Okay, so before we end this part, I also want to showcase a interesting analysis, which is the scaling law. So we all know this scaling law of large language models like GPT proposed by OpenAI, which says basically if you just increase your compute or increase your data size or increase the parameter of your models, the loss or the actual performance measure of the model will have a linear log relationship when you increase either the compute or dataset size or parameter size. And this is pretty important for modern machine learning as it gives us a recipe for training your model. And you don't need to do any more like sophisticated modification, but just adding more compute and data, you achieve better model. And we want to examine like whether we see this plateau of the sensor LM model, because we are able to collect this wearable data almost every day, and we're generating these insights. Like even like right now, like in real time, we're generating a lot of sensor data with a lot of insights. So with our current data size, we show because we don't have such a test loss as a measurement, and instead we show this activity zero-shot prediction as a proxy for measure our model capability. And we show this scaling pattern also across this compute and data size and model size dimensions. And as this graph shows, although we see the increasing trend is slowing down as we increase either those dimensions, we're still seeing a going up trend, which means if you increase your data size, your model size, or even your compute just by training longer, we'll ideally see the model capability will become better and better. And this is really exciting as we don't see this plateau of the model, which means we can leverage this data we'll generate in real time or in the future, and we can in turn feed this data to train better version and better outcome of this model. All right, so I almost covered these two ongoing directions in our lab, and you might ask, okay, what's next? What's the future? So let's talk about some future directions in this space. So we have been talking about specific domains for data modality, like wearables, breathing data, sensory data. And so I would say each of these modality, or even health modality or medical modality, is trying to tell you something about the patients, either in a very fine-grained manner, either in the expression level, or you can also measure, for example, the radiology experts would measure like medical imaging, genetics experts would measure the GWAS, and we are generating a lot of aspects of your health and medicine. And each of them will give you very important information, but in some sense, I would say they're a little bit limited. And by incorporating all this information together, we will be able to precisely recover the holistic picture of the patient health. So another ongoing work we're doing is we're trying to build this foundation model for a specific modality, which is the sensor modality. And even beyond the sensor modality, if you can have, for example, the sleep data, your EHR data, your genomics data, and pathology, radiology, etc. And with all of this, a North Star we want to build would be a multi-model health world model that captures this holistic information and can reason about each aspect of the information provided by the patient. And we can even take a step further, and by leveraging language as a shared general modality, one can build this interactive agent that can reason about your health data from different modalities and provide health insights. In another ongoing work, we're building a personal health agent that can reason over one's wearable, EHR, and daily conversational data. So it has a real-time UI for conversation and interaction. And for example, the user asks, okay, you have access to my wearable data and my EHR data. I'm worried about my sleep relative to others in my age group. So what is my average sleep, and can you give me some recommendations? So the agent would then leverage external memory and the resources and also the data access of the patient and reason about their personal data and present insights. For example, it will give a thought period to say, okay, if we want to give sleep recommendations, I will need to search and also calculate the sleep statistics from this person's history. And then it will conduct an action, which is search and have an observation of, okay, more than 7 hours sleep per night is a recommended sleep. And then go to the data of the patient to see, okay, what is your average sleep over past 30 days? And it will then do the code generation to analyze your sleep data and get the statistics and then give the final answer. And based on this cycle, it will build the first step towards this personal health coach with merely your mobile devices and making it more universally accessible to everyone. Okay, so before I end this talk, I hope this is exactly at the 15-minute hallmark. And I would also like to thank my exceptional students and collaborators, and really excited to build close collaborations within UCLA. And our lab is also hiring PhD students, postdocs, and interns. So if you're interested, feel free to reach out. Okay, with that, thank you all for listening.